Welcome back. This is Larry Benko, callsign W0QE. And this video is about designing crystal filters and using SimSmith to analyze the design so that the resultant filter that we build is quite close in performance to what you designed. Crystal filters are a little bit tricky to design in that the crystal itself may not be matched to another crystal, even though they have the same frequency. And as an example, I made these measurements on some groups of crystals a while back. And if we look at for this example today, I'm going to do a design a filter around 14.318 megahertz crystals. I measured 30 crystals. The overall frequency difference was 200 hertz, which is pretty small. Yet the resistance in the crystals varied by over a factor of 2. The motional capacitance or the series capacitance varied by quite a bit, and the parallel capacitance varied by some. So these crystals are not identical in any way, shape, or form. And the programs that we use to design a crystal filter typically expect all crystals to be identical. They don't really care what the parameters are, and they'll let you put the parameters in the program, but they almost always assume that or let me say this, I've never seen a program yet that would accommodate different crystal parameters in different positions. So with having said that, we need to come up with a plan as to what we can do. So let me use this as a plan here for a moment. As a proposed plan, I always hate when people tell me how to do something, but with that being said, let's at least come up with a plan that's at least loose. And most of these things need to be done along the way. You don't have to do them in the exact order I proposed here by any means. Certainly your skills are different than my skills. What test equipment you have may be different than what I have. We're all different. So in order to try to accommodate more people, let's at least use this as a starting place. Before you can start, you have to determine a source of crystals. That should be obvious to everybody. They need to be at the right frequency or pretty darn close to the frequency. They can be moved a little bit in a design, but not very much. And you need a source of crystals that includes more than the number of crystals you're going to use. You really need to have a considerable number of additional crystals. If I was building one filter, I'd probably buy double the number of crystals that I thought I needed. If I was building two, I'd buy maybe 25% extra. If I was going to build 5 or 6 filters, I'd only need to buy maybe 10 extra crystals because you can sort them in groups and stuff. But you need to determine a source. Crystals usually cost something around 50 cents a piece if you buy a fair number of them. Lots of surplus places have them. The conventional manufacturers have them, etc., etc. You can even go to a crystal place and they may have overages that you can buy certain frequencies. And based on what your use of the crystal filter was for, you may not care about the exact frequency. In some cases you do, some cases you don't. But you got to determine, where the crystals are going to come from. Before you design the filter, you need to buy the crystals because you need to measure the parameters. So we talked about in the previous video measuring the parameters and putting them into a table. If I was doing it as a suggestion, I'd put them into a format that I could read into Excel. And the advantage of reading them into a spreadsheet is that I can then sort them on different parameters. So it makes it a little bit more convenient, particularly if you have a fairly large number of them you've scanned. Third, you need to design a filter using any program that you wish. And the program is going to ask you for the values of the crystal, and you need to put in some kind of average of what you think the value is from what you've scanned in the crystals you're going to use. This is not a big decision to make. Just roughly come up with an average and use that as a starting place. Then you need to come up with a plan for non-identical crystals. Which of these crystals that are not identical do you intend to use? Then we're going to compare the output in SimSmith, and we're going to play with it a little bit, and we're going to iterate back and forth a couple times and be done. As you get better, you really don't need to iterate much. And I can come up with some suggestions that will help you so that you put the crystals in the crystal filter in such a manner that you don't need to change the components very much. Then maybe we need to include the parallel capacitance to the crystal case in our design. A crystal is not a two-terminal device as you typically think of it. It's got a case on it, and the case may be connected to ground. And in the case of building a crystal filter, you want to solder the case to ground to minimize the coupling between crystals. Doing that makes the crystal a three-terminal device, and a little bit of the parallel capacitance goes to the case. You might wish to include that. Certainly, it's easy enough to analyze whether it's a big deal or not, and you can decide what you want to do with it. Finally, we need to match the filter to 50 ohms. Crystal filters are almost never 50 ohms when they're designed. And the reason for that is pretty simple. In an LC type filter, you buy the inductor and the capacitor separately. In a crystal filter, what you're buying the product of L and C. Because the crystal filter is specified on frequency, it's not specified on emotional capacitance or inductance. Finally, we build the filter, and hopefully, if you've you had a good plan along the way and you've analyzed it well, you'll get a result that's very, very close to what you expected. And that's obviously the goal. The goal is not to build the filter and have to rebuild it 4 or 5 times. Several years ago, I did a bunch of crystal filter design, and I used a program called Filter Design. It was written by a guy named Neil Hecht, who unfortunately has passed away. He ran a company called AADE, stood for Almost All Digital Electronics, and he made an LC meter kit that was $100, and it was very nice. And I actually have 2 of them, and it works very, very well. And through that program, through the website attached to the kit, I saw that he had a filter design program. The filter design program in those days was a little bit more rudimentary, but over time he improved it quite a bit, and version 4.5 is the latest version. Since he's passed away, there are several websites that host the program now, and a search for it on Google or whatever will certainly give you a lot of hits where you can download it. It's a very comprehensive program. It designs an awful lot of filter types, both LC, crystal, but it's a little hard to use, and it's extremely hard to do what-if cases. When you design a filter, if you want to go back and say, I want the same filter again, but just a couple parameters changed, or just one parameter changed, it forces you to re-enter everything. Because of that, it's not very friendly in terms of trying to see what's really going on, but it's very comprehensive. Recently, I've been using a program by Horst Stettler, DJ6EV, called Crystal Ladder Filter Calculator, and it's an offshoot of a QEX article in 2009, which is available on the ARRL website. This program is much simpler. It has fewer features, but it's a lot nicer to go use if you want to understand how things are working. I also did some previous work. It's on my website using the filter design program at the top, if anyone's interested. In this window, we have 2 things showing. In the background, in full screen, is a SimSmith Circuit. The SimSmith Circuit shows a 5th order, or a 5 crystal filter, and the associated components that go with it. Each crystal is in a ruse block, and it shows on top of the SimSmith program is the program we're going to use to design a filter. This program was mentioned before. It's a free program available on the web from DJ6EV, and the SimSmith file we have here matches the results of this. What I asked for was a crystal which had the characteristics of 18.8 femtofarads for emotional capacitance, 14.318078 megahertz series resonant frequency, 4.146 picofarads parallel capacitance, and I wanted a crystal filter that was 4 kilohertz bandwidth, 0.01 dB, a ripple, and Chebyshev design. And the plot here is shown over plus or minus 10 kilohertz from the center frequency. And the reason I use this program rather than another program is because I can change these parameters easily and you can see what goes on here. This program, of course, has a very huge limitation, and that is it expects the crystals to all be identical, and it expects the crystals to be perfect. Notice there's no loss in the passband, and that's not what SimSmith predicts. But nevertheless, this is what we got. And this program also does not show you what the SWR of the filter is. It does show me that the impedance of the filter is 202 ohms, which I've put here, and then I've used this F block to control the generator and the load at the same time. And I did that by, the circuit here doesn't even care what the load impedance is. The F block is just is the value. The generator is terminated in the same impedance, so it's same impedance. And this just allows me to control all the crystals at the same time. I can get rid of these commands later, and we'll do some stuff along the way that makes the crystals different. But for the moment, right now, they're all identical. And here's what we get. We get a filter that looks very, very nice. Very low SWR, considerably less than 1.1 to 1 in the passband. It's like 1.08 or something in the passband. Has a passband that's fairly flat, a little bit of roll off on the ends, and it's 1.44 dB down, given the crystals that I put in here. Now, I put the exact same crystal parameters here that I put in the program, except I included the resistance, the average resistance that I had when I measured them, where the program here assumes it's 0 ohms. Now, let's see how we could change this filter a little bit and see if we like it better or worse. You might say that passband ripple is awful small at 0.01 dB, and you'd be right, it is pretty small. So what we're going to do here is we'll make it 0.1 dB. And let's watch the skirts of the filter change when we do that. So we gained about 5 dB here, and we gained a couple dB here. And that looks pretty good. Let's continue on. Let's go to 1 dB. We gained even more. So as we allow the passband ripple to, now we start seeing the effects of the passband ripple. As we allow the passband ripple to rise, we see the skirts dropping. You say, I want that filter because I don't care if it has a little bit of passband ripple. Maybe you do, maybe you don't. But there's some downsides to this. Let me load a couple other SimSmith files and we'll show this. If I load this one, and again it stays behind here, this one matches this filter, which was the 1/10 of a dB ripple. Notice what happened to the passband SWR. Passband SWR went from less than 1.1 to 1 to just about 1.3 to 1. And let's see what happens when I change the opening. Sorry about that. Here's what it looks like with the 1 dB ripple. Now, we see a ripple in the passband. Our ripple does not look the same as the ripple in the circuit in the design program because of the fact that the crystals were not zero ohms of resistance. But look at our passband ripple. It's over 2 to 1 SWR. Personally, what I gained here is not that much. I went from 60-some dB to 80 at a 10 kilohertz spacing. This is a 20 kilohertz bandwidth. This is 20 kilohertz. This is centered. This one's close to centered. It's not exactly centered because as I play with stuff, the center point moves around a little bit in the filters. But it's roughly the same. And I don't like this filter particularly. For my liking, I would go back to the 0.01 dB filter, ripple filter. And if I really wanted to have better performance, I would do something like this. So I put, now to add an extra crystal. That gives me this better performance than the 1 dB passband ripple for adding extra crystal. So that's something to be considered. On the other hand, I'm running out of space up here unless I want to include the crystals in the ruse blocks and stuff. So let's go back to 5th order filter. But for if you're building the filter yourself, the 6th order filter starts to look very nice with a lower ripple. The advantage of having the lower ripple is pretty simple, and the reason that it's nice. Let me get back to my original circuit here. The reason that's nice is SWR shows what's going on in the filter as I'm adjusting the components much better than the passband does. The passband doesn't move much and the SWR can move quite a bit, so you can see what you're doing when you're adjusting it. So this is just a piece of information. Now, what if we want the filter to be a little bit narrower in bandwidth? Let's make it 3 kilohertz. What happens to our circuit? Well, we have better skirts, and what happens to our circuit? So let's look and see if we can find. I I made all these circuits in SimSmith. I just have to remember which ones they are here. I think this one here is the same. Yes, it's 3 kilohertz bandwidth. And what we're seeing here now is the bandwidth here is the passband increased. The passband increased, the loss increased in the passband. It was 1.4 dB before, it's 1.9. So asking for the filter to be narrower will always give you more loss in the passband. The impedance it matches changed, and I've matched these again at the same time. I've done a lot of work in here. Each time I change one of these things, I've gone in and filled in all the values. And if I was to do this in a video, it would be incredibly laborious. I'd make a whole lot of mistakes along the way, and you'd probably get bored with it pretty easily. So making the bandwidth narrower increases the loss. Making the bandwidth narrower basically may or may not be what what you want. So, that's kind of your choice. Let's go back here to the same bandwidth we had before, and now let's change the emotional capacitance. Let's go from 18.8 femtofarads to 17.8. It turns out changing this from, let's just leave it like here, right? It's 4 kilohertz, go from, and just watch this curve as I change it from 17.8 to 18.8. It changed just a teeny bit, but it did change these numbers a lot. It changed the impedance. This is 200 ohm, 200 ohms that we matched to. This is 216. These values all changed down here. So it really doesn't matter what the emotional capacitance is in designing the filter. But that does not mean that you can have emotional capacitance be different in all 5 of these crystals. If you do that, you'll find out that the results are pretty ugly. So that didn't change things much. And again, we can load that in SimSmith here. Again, if I can remember which ones, I think it's this one here. Yes. We see the same 1.1 to 1 or less SWR, the same kind of passband. In this case, the passband loss is 1.36. So having a lower emotional capacitance seems to make the insertion loss just a little bit less. But it went from 1.44 to 1.36, which is very, very small. So let's do one more thing, and then we'll start playing with the actual filter itself. And the next thing we're going to do is, what if we change this? Let's change this back to 18.8 again. And let's change our capacitance here, our parallel capacitance from, say, 4.146 to 3.146 picofarads, and see what that does. Now, that changed this again, too, a little bit. The slew, the difference between the left and right sides here drops as the parallel capacitance drops. However, it is what it is. You can't do anything about this. This is just building the crystal gives you the parallel capacitance. But let's see what the SimSmith file that goes with it looks like. Oops, I'm sorry, I did that. I don't want to save that file. I want to load a file. Okay, 3.146 picofarads. Again, it looks the same. Nothing special, at all that's going on. You can have any of these values will give you an adequate filter. Now the problem seems to be that, let me just minimize this and get this out of the way. Let's go back to, I'm going to go back to the original circuit that let me control things. Leaving all my components alone here for the moment, and going over here to this F block, I can control the emotional resistance, capacitance, inductance, parallel capacitance for the holder. All that stuff can be controlled in here, and all the crystals will be identical. And this is, again, one of the powers of SimSmith. So let's go over here and let's watch this filter. And this is the original one. It was it says 19.8 femtofarads there. That is an incorrect number, because I really should just basically get rid of all this here, because this allows us to change all these things. So it's not what they are necessarily at the moment. The values that we picked here for the capacitors and stuff were for the 18.8 femtofarad, 4.146 parallel capacitance, and 14.318 megahertz center frequencies. So let's now take the motional capacitance and move it down by 1 femtofarad. It didn't hardly change the filter at all. It made the filter a little bit narrower in bandwidth, and it moved its frequency down just a teeny bit, a couple, maybe 100 hertz at most. So the motional capacitance has very little effect on the crystal itself, a crystal filter itself. Maybe. And we'll come back to that one. How about the parallel capacitance? Let's move it by a picofarad. Picofarad lower in capacitance, increased the bandwidth a little bit. Picofarad higher in capacitance, narrowed it a little bit. Again, very little change. What about the resistance? I'm going to go from 7 ohms to 17 ohms. Now, that has an effect. That makes our loss go from 1.4 dB down to 3.35. You may not care, but it means that we had crystals that had Qs of 80,000 before. Now they only need to have Qs of 34,000 to give you this performance. If we keep increasing the resistance here, what we'll say is the filter just gets rounder and rounder and rounder. Pretty soon it has really no flat pass band at all. The SWR, though, still is very, very good. So, having said all this, you might draw the conclusion, and it would be erroneous, that it really doesn't matter what you put in here for the crystals. So let's prove that that's really the case. Now what we're going to do is to take the existing filter that was created by this design program and subsequently put into SimSmith with the addition of the actual loss of each of the crystals. And we're going to vary this crystal X5, and we're going to vary its parameters and try to compensate for those parameters while we leave the other 4 crystals unchanged. This program assumes some things. First of all, when it designs a filter, it assumes crystals 2 and 4 are the lowest frequency crystal frequencies. Crystals 1 and 5 are pulled higher by 1115 hertz, and crystal 3 is pulled higher by 485 hertz. And that's a calculated value based on bandwidth you ask for and the crystal parameters, etc., etc. But nevertheless, that's what it's trying to do. So if we take this base crystal here and we drop its F sub s by 1,000 hertz, we will then need to raise its frequency by 2,115 hertz, hopefully, and we'll end up with the same approximate circuit. So let's try some of these cases. Then we'll raise the frequency of this too. We'll vary this, the motional capacitance, we'll vary the parallel capacitance, etc., and we'll see which ones are easily compensatable and which ones are not. So to begin with, let's drop the frequency 1 kilohertz. Okay, we dropped the frequency 1 kilohertz, and what we notice here is where we needed 104 picofarads over here to raise this crystal's frequency 1,115 hertz. We now need 52.9 picofarads, a smaller value, to raise this crystal by 1 kilohertz plus the 1,115 hertz. And when we do that, we see the passband SWR came up a little bit, not much, but just a little bit. Above the dotted line was basically the passband minimum before, which was 1.09 to 1. It came up a little bit, but it looks very, very good. So this did not hurt us very much in the design at all by having this frequency need to be raised by an additional kilohertz. Now let's try to see what happens if this crystal already is high in frequency. Okay, here's a case where it was 500 hertz high. At 500 hertz high, we don't need to pull it as much. We see our capacitor being increased from 104 picofarads to 191 picofarads, indicating we are not pulling it as far as in frequency. Our SWR is very, very good, down to the same SWR we had before when this was at the same frequency as the other 4 crystals. This is excellent. Let's do it again. This time we're going to go to the full extent. We're going to find a crystal, hopefully that's 1100 hertz, 1115 hertz high, which means we need no capacitor. No capacitor. SWR is still very good. Passband's very good. This is wonderful. We got rid of a component, and we used our crystal that was way off frequency from the other ones just fine. But again, we're assuming it's got the same parallel capacitance and the same motional capacitance. Continuing on, the next thing we're going to do is we're going to bring the frequency back to the nominal frequency, but we're going to change the parallel capacitance to be 1 picofarad less than we had before. So, used to be 4.146, it's now 3.146. We can see that if we change this capacitor just a little bit and change none of the other capacitors, we can get the SWR down again to the same level we had before. That's very nice. That means that we can compensate for a small amount of change in parallel capacitance. We can't turns out we can't compensate for a large value of change, but it turns out the parallel capacitance is never that big of a change anyways. It's pretty much standard in all crystals, somewhere around 3 to 5 picofarads. But nevertheless, we could change it. If we made this go back to 104 picofarads, which is what it was initially, we see the SWR wasn't quite as good. This change was, let me say it was cosmetic mostly. Likewise, if we bring a circuit in where the parallel capacitance has been increased 1 picofarad, we see that we dropped this capacitance just slightly from the 104 picofarads, and it's still pretty good. This is a little bit higher than it was initially, but not very much. This is still very good SWR. Let's continue on. The next thing we're going to do is we're going to bring in a crystal into this circuit which has 2% lower motional capacitance. And again, we change this one capacitor just a little bit, and we can tweak on the SWR a little bit, and this is still pretty good. 2% low. Very, that's not a lot low. It went from 18.8 to 18.4. And if we remember, let me bring up this table. I had variations way more than that. The assumption would be that you would take these 30 crystals and you would bin them accordingly so that the ones you were picking from wouldn't have variations in motional capacitance over this large extreme. They would have smaller variations. So I went 2% low in this case. Let's go 5% low and see what happens. Now we start to see that we can't compensate for it completely at all. If we start changing these other components, we end up hurting these other crystals down the line. And this is what we get. So 5% change we could tolerate, perhaps. It's not bad. It'd be nicer if it was a little bit better than that. Let's go on the other side and see what 5% on the high side looks like. "5% on the high side didn't seem to hurt us much at all when we increased this capacitance a little bit. So fundamentally, what this is telling me is that it's kind of important to match the motional capacitance. It's more so almost than frequency. With frequency, we've got a couple really nice choices, and that is if we can come up with two crystals that are pretty much the same frequency and lower in frequency than other ones, we can raise these up by a variable amount and be in good shape. So let's go back to the original circuit again. In this case, we're going to take one of these two capacitors that were the base frequency and increase or decrease their frequency just slightly and see what the effect is. I've got SimSmith set up here to where it's 1e to the minus 4, or basically it's 100 hertz steps. So if I vary this 100 hertz, that's what we see. You can say, maybe it's not a big deal. Maybe it is a big deal. nominal frequency plus 100 hertz, nominal frequency minus 100 hertz. These two crystals should be matched pretty closely. Let's take this crystal, drop it 100 hertz, and put a small capacitor in series with it and see if we can at least correct it somewhat. As we start to correct this, we'll be messing with these values here too, so we have to be careful. But we know this should be, should be a pretty large amount of capacitance because we don't have to go very far. And see if this gives us some help, or if it's just kind of a waste. And the answer is absolutely not. This is worth something. So if you're off 100 hertz on these two base crystals, 1,000 picofarads here will get us right back to where we were before, when this was the right frequency. So these do not have to be matched super accurately. So we say get these matched within 100 hertz, maybe get them matched within 50 hertz. I mean, you can. Here's where I don't want to be giving advice on what to do, because everyone's tolerance for how they do things is slightly different. What I'm saying primarily is, if you want this to be as good as possible, there are things you can do that make the job easier. And starting with these two crystals being the same frequency means you don't have to worry about any capacitance in series with them. They're both the same. If you need to correct them, they can't be corrected very much. I pretty much can guarantee you that if we made this one, say, 200 hertz low, I don't think we can correct for that as well anymore. Let's just see. Oops, did it again. Going the wrong way. Well, I'm kind of wrong on that one. Let's go a little bit higher yet. 300 hertz. That's correctable too. So this pretty much says to me, if I had crystals, I'd sort on C sub S primarily. I'd take the two lowest in frequency that were pretty close to the same frequency together, because you don't want to correct these too much, I don't think, crystals 2 and 4. And I'd pick those, and then what I would do is to make these crystals, hopefully I could find some that would be a little bit higher in frequency, and I just adjust those up. Let me try that here and come back in just a moment with an example. Well, that was remarkably easy to do. I took this, I just randomly picked some numbers here. I said that crystal X2 would be at the lowest frequency for the filter. This crystal was actually lower than that, so I needed to correct it, even though these two are supposed to be the same. So this one was 100 hertz lower. I corrected for it. I said this one was 200 hertz above the base. This one was 600 hertz above the base. This one was 300. And I adjusted this capacitor based on, for this one, I adjusted this capacitor for this crystal, and I adjusted this capacitor for this crystal. And I got the SWR that looks very, very good. Passband looks very nice. Everything looks good. This was all based on all having the same parallel capacitance and all having the same motional capacitance. It turns out I went back and looked at my scan of 30 crystals that I had from previous time, and I was able to find 5 or 6 crystals that were 18.8 plus or minus like 0.1. So that's almost nothing. So if we go in here and do something like, say, make this point 18.7, make this, say, maybe 18.9, maybe make this one 18.9, maybe make this one 19.0, say. We haven't changed things hardly at all. There's a little bit of SWR rise there. I don't know if we can fix that real quickly or not. I don't know. You could play with it a little bit more. This again is still incredibly good SWR. And these crystals, if you were to look at these based on something you had, so you scanned them all and you made a table, you would not have picked these crystals. Let me say, I would not have picked these crystals some time ago. I've learned over time that the frequency is easy to correct. The other internal parameters are not as easy to correct. But if it was me, I think that I would do something like this. This gives you a reasonable way to build a crystal filter that was very nice, has good performance, and when you build it, you'll find out that it works quite well, assuming that you've included all of the circuit that you're actually going to build in SimSmith, and we'll get to that in just a moment. Let's now try to take into account the effect of grounding the cases of the crystals. We know we need to ground the cases of the crystals for good isolation and good stop-bend attenuation, but we also know that the crystal that we measured as a two lead part really has a third lead, and that's the case. And we're now connecting that third lead, so it's part of the circuit. The 4.146 picofarad capacitance included a capacitance from the crystal to ground to the case, a capacitance from the other lead to the case, and then a capacitance from the one lead to the other lead. So and I've measured a bunch of these over time, and you can measure them with a capacitance meter very easy. Just take one of the crystal leads and measure to the case. You get about a picofarad from each lead to the case. So let's see what that does to a circuit. What we would do is we'd put an extra 1 picofarad capacitor in here, and then we have another 1 picofarad over here. So that means we need to increase this capacitance by 1 picofarad. It also means now these two 1 picofarad capacitors in series become half a picofarad, so that this capacitance needs to be reduced by half a picofarad. 1, 2, 3, 4, 5. Okay, that's half a picofarad less. And then we need to proceed down the line and do that to all the cases. So let's And this is a really nice part of SimSmith. You can see what you're doing while you're doing it, which is really nice. So now this capacitor contributes another picofarad from each lead to ground. So let's increase this capacitor 1 more picofarad. This one gets increased 2 because this crystal and this crystal. This one over here gets increased probably 2 because this 1 picofarad is in series with 200 picofarads. So let's increase it by 2 also. Increase this by 1. And then we need to add 1 more capacitor over here. That's a 1 picofarad capacitor. Oh, I did that wrong. Let's hit wrong. 104 picofarads. This is the one that becomes 1 picofarad. Sorry about that. Okay, and there's our new response. It's not quite as good as it was before, but it's pretty close. You might say, why did you increase these by 2 picofarads? Shouldn't they have been reduced then? Sorry about that. Shouldn't they have been reduced because the additional capacitance from the crystals? Well, if we try to reduce them, let's see what happens. We could reduce this to 2 picofarads. Maybe that helped. I don't know if it helped or not. Let's go maybe just 1 picofarad of the way. Maybe that helped a little bit. Hard to say. It's really hard to say whether these changes are so small that they're hardly worthwhile. So for the most part, unless you're really doing something critical, the capacitance that you get across the crystal, trying to attribute part of it as a capacitance to ground makes much less effect than a lot of other things you can do in the design. So if it was me, I might reduce these capacitors, these shunt capacitors, by a picofarad or 2, but the effect is hard to argue that it has really any real merit. Now we're almost done. There's one more step to do, and for the final step, unless you are very, very lucky, we probably need to match the impedance that the filter turned out to be to the impedance that we want to use the filter at. In this case, the filter turned out to be a 202.8 ohm filter, and we probably want to use it at 50 ohms. Often, though, inside a receiver, you might want to use the crystal filter at higher impedance. But generally, you will need to match the filter to some other impedance other than what it turned out to be. So what I've done here is take the original filter I had, and I just created a giant ruse block with the filter in it. The component values in the filter that are shown right here are the standard values we've been using. They were the base values. I included all the components in the filter, the 1 series component capacitor, the tuned capacitor C3, but I left off the 2 outside capacitors, and that'll become obvious in a minute. So I checked that, I did that circuit, I checked it with a 202 ohm load and a 202 ohm source, and we see this nice SWR, the good passband. Passband loss is 1.44 dB, which is what it was before, proving that this circuit indeed does what the previous circuit did that was spread out over multiple blocks. So now what we're going to do is we're going to match this. So the simplest way to match this, there's several ways to do it, but let's start off by putting a 50 ohm load here. That will be our terminating impedance. And let's put an automatic matching L network in here. Our automatic matching L network, though, needs to match to 202.8 ohms. And here it did it. And what we see is, again, a good SWR at the input, and we see a good output. We see a little bit of loss here, 0.04 dB, probably due to the inductor in our matching network. And let's follow this circuit with another one on this side. The one on this side needs to be nothing done to it because it'll match to 50 ohm. It'll match to 200 ohms as it is. But what we're going to do is we want to force it to 50 ohms. Now we can either put a 50 in here, but then we won't read SWR properly, or it's just easier just to change our generator type to 50 ohms now. This will adjust itself, and here we are. Not quite as good as SWR as we had initially, but it's pretty close. We have some problems in doing this in that this is matching at one frequency only in this range, and there is loss in these inductors. But this is still a very good SWR here. So what do we need to do now beyond this? Well, there's a couple things we can do. One thing we can do is say, why do we need to have this capacitor in our filter? This capacitor is a kind of a, is it needed? It's external to the filter here. It was in series with the capacitor before, in series with the crystal before. Why don't we just get rid of it? We can get rid of it by instead of matching at this point right here to 202.8 ohms, we can match to 202.8 ohms less with the effect of this. So this capacitor adds 106.86 ohms of capacitive reactance. Why don't we just match at this point to 106.8 ohms of capacitive reactance and dispense with this component? Let's see how that works. So we'll set this to match to 106.8 ohms of capacitive reactance. And of course it's not going to be very good, but we're going to get rid of this part now. And there we are. Matched very nicely. Well, that's kind of cool. Let's do it on this side too. So we'll get rid of this component. And this side we don't need to change play any games. We're just going to match from whatever impedance we get here. And be done. And then we can dispense with that those two components in our filter. And there we are. Now, we have two supposedly identical matching networks here, but they're a little bit different because of the loss in each one of them. If we flip this circuit around, we would see a slightly different SWR again. It's probably nice to make these be the same circuit. They're so close to being the same circuit, you probably can't build a circuit that's, distinguishes one from the other yourself. So if it was me, I would just, set this one to be, say, manual. Let's make it match this other one and see what happens. And something like that will probably, be pretty darn close to what we want. 109.72. And sure enough, that's actually a little better than what we had before. So it's symmetrical again. Now, the filter that you end up with may not have symmetrical capacitors on the input on each end of the filter, in which case then you can't make these two the same. They'll be slightly different if you want to include the capacitor. But including the capacitor is something that's generally done in industry. It's a component that's saved. it really didn't change the value of the components a lot. It changed them a little bit. It didn't make this matching network be more expensive or less expensive or anything. But this would be the final result. So it would be these two matching networks tied on the end, and then this thing in the middle, which is our 5 crystals and our 4 shunt capacitors and our 1 series capacitor here. And we're done. And if you build this, you will probably be quite happy with the results. Now, it does mean that you're required to be able to measure the components that you're putting in for the external capacitors accurately. And it does mean that you had to have measured the crystals accurately. But today, with the little network analyzers that are available and a little bit of care, it's pretty easy to do. So hopefully this has been an interesting video on how to build crystal filters. I use them pretty regularly for enhancing the quality of spectrum analyzers, particularly for making transmitter phase noise measurements, oscillator phase noise measurements. I use them other times to increase the dynamic range of a spectrum analyzer. And, it's another tool in the arsenal, and it's a good use of SimSmith, which without SimSmith, it would have been much, much more difficult to have figured out what capacitance it took to change the frequency of the crystals. It would have been much more difficult to have done the matching. It would have been more difficult to initially have come up with the parameters for the crystals. So this is another good use for SimSmith. Now, SimSmith had a couple weaknesses in the whole process along the way, but primarily those dealt with the fact that when you click on someplace on the plot here, you're only afforded a 3-digit accuracy in the frequency. And as I showed in the earlier video, there were ways around that. So that was a very minor inconvenience, but nevertheless, SimSmith is quite useful in this kind of an environment. Thank you very much, and hope people have enjoyed this video.